Everyone, this is Bhumika Mohan. In this video, I'm going to talk about a topic related to discrete mathematical structures, that is properties of groups and subgroups. So the contents of this video are, first I'm going to give an introduction and then talk about properties of groups. Then I'm going to talk about properties of subgroups and its examples. And lastly, I'm going to give a conclusion. So coming to introduction, in mathematics, the concepts of groups and subgroups are fundamental to the field of abstract algebra. A group is a fundamental algebraic structure consisting of a set equipped with a single binary operation that satisfies certain properties. A subgroup is a subset of a group that is itself a group under the same operation. The groups and subgroups have various properties that define their structure and behavior. Coming to properties of groups, a group is a set G equipped with an operation that combines any two elements A and B to form another element denoted A star B. The operation will satisfy four conditions called the group axioms. The first one is closure. For every pair of elements A and B in G, the result of the operation A star B is also in G. That in symbolical form is for all A, B belongs to G, there exists A star B that belongs to G. Second one is associativity, which tells that the operation star is associative, meaning for all ABC in G, A star B star C equals A star brackets B star C. This in symbolical form is for all ABC belongs to G, A star B whole brackets into C equals A star whole brackets B into C. The third one is identity element, which tells that there exists an element E in G such that for every element A in G, the equation E star A equals A star E equals A holds. This can be told in the symbolical form as for some E belongs to G such that for all A belongs to G, E star A equal to A star E equal to A. The fourth one is inverse element, which tells that for each A in G, there exists an element B in G such that A star B equals B star A equal to E, where E is the identity element. This in symbolical form is for all A's belongs to G, for some B belongs to G such that A star B equals B star A equal to E. Coming to properties of subgroups, a subgroup H of a group G is a subset of G that is itself a group under the operation defined on G. For H to be a subgroup, it must satisfy the following conditions. The first condition is non-empty, that is H is non-empty. In symbolical form is represented as H not equal to null. Second one is the closure property that tells for every pair of elements A comma B in H, the result of the operation A star B is also in H. This in symbolical form is represented as for all A comma B belongs to H, A star B belongs to H. Coming to the third property, that is identity element, H contains the identity element of G. This in symbolical form is represented as E belongs to H. Fourth one is the inverse element, which tells that for each A in H, the inverse of A which exists in G is also in H. This in symbolical form is represented as for all A belongs to H, A inverse belongs to H. These conditions imply that a subgroup inherits the associative property from the parent group G. Coming to this, alternatively, a more compact way to verify if non-empty subset H of G is a subgroup is to check. First one is the closure under the group operation, that is, for all A comma B belongs to H, A star B belongs to H. And the second one is closure under taking inverses. This tells that for all A belongs to H, A inverse belongs to H. Some of the examples are, example of a group is the set of integers z with the operation of addition forms a group. The identity element is 0 and the inverse of any integer n is minus n. Coming to the example of a subgroup, the set of even integers forms a subgroup of z under addition. The identity element 0 is in this set. The sum of two even integers is even, that is closure, and the inverse of an even integer is also even. So coming to the conclusion, these are the fundamental properties and concepts related to groups and subgroups in mathematics. These properties and concepts form the foundation of group theory, a central area of abstract algebra with applications across many fields of mathematics and science. Thank you.